22nd of July, something extraordinary happened in Northern Virginia. A transmission fault disturbed the voltage. A cluster of data centers protected themselves, and within seconds, roughly 3 gigawatts of demand disappeared from the grid. Now the system recovered, but that successful recovery contains a warning. According to the available public reporting and Ting Labs measurements, a Dominion Energy transmission line went out of service at 7:56 in the morning. Subsequently, voltage sags appeared across Northern Virginia, and a cluster of large computational facilities transferred from grid supply to backup power. Approximately 3 gigawatts of demand then disappeared almost instantaneously. Frequency rose across the Eastern Interconnection. The strongest effects lasted about 2 minutes, and the wider system settled over roughly 10 minutes. The public account is still emerging, so it's not an attempt to allocate blame or claim a final cause, but it is an attempt to understand the system behaviour that the measurements already make visible. In engineering terms, the sequence is simple. The transmission fault depressed voltage. Facility protection detected a condition it was designed to survive. Critical load transferred off grid. Demand fell much faster than generation could change. So generation temporarily exceeded demand and the frequency rose. The grid's controls and operators then damped the deviation, and no cascading blackout occurred. That's a success. But successful recovery should not make us ignore what the system had to absorb. The initiating event was a transmission fault. The transfer of the data center load was a second disturbance, one created by many assets making the same locally rational decision at nearly the same time. The question is not whether the protective systems worked, they did. The question is whether the whole system consequence of their shared action had been understood, modelled, and assured. Inside the asset boundary, the protection did exactly what its owners needed. Equipment was protected. Digital services continued. UPS systems and backup generation operated. The local objective was achieved. But at the system boundary, that same protection had created a second disturbance. Load vanished. Frequency rose. Voltage conditions changed. A shared response propagated far beyond the facilities that initiated it. Now hold that thought and look back to the Iberian Blackout of the 28th of April 2025. The final ENTSO-E Expert Panel report describes an interacting sequence, oscillations, gaps in voltage and reactive power control, output reductions, generator disconnections, and a final cascade that separated Spain and Portugal from the continental European system. The decisive weakness was ineffective voltage control. Its consequence was an uncontrollable rise in voltage. As voltage increased, more generation reduced output or disconnected. Synchronizing torque fell. Frequency collapsed and the system blacked out. The report also shows how constrained some of the available steady-state voltage control margin was. Between 1232 and the blackout, 58% of Spain's shunt reactor capacity was connected. In southern Spain, the figure was as low as 32.5%. Now, those figures are not the whole cause. They're evidence of a system entering a dynamic event with limited room for error. Put the two events side by side and they appear to be mirror images. In Northern Virginia, load left. Generation temporarily exceeded demand, so frequency rose. In Iberia, generation left, demand exceeded generation, so frequency fell. The events aren't identical, and the plotted amplitudes are not directly comparable, as you can see from the slide. But the engineering blind spot's the same. The grid does not see the intent of an owner, a protection engineer, or a software designer. It sees the aggregated behaviour of every connected control system. When enough assets make the same decision at the same time, the system experiences a new disturbance, whether the assets are consuming electricity or producing it. Now, when I began examining the Iberian event, I expected low inertia to be the main explanation. That seemed plausible. A system with fewer synchronously connected machines has less immediate resistance to a frequency change, but the final modelling changed my view. The expert panel estimated a plausible total inertia range of about 2.21 to 2.71 seconds. It then tested a case with 20% more system inertia. The added inertia changed the frequency trajectory, but it had minimal impact in the final moments and didn't prevent the collapse. The decisive weakness was ineffective voltage control. Its consequence was an uncontrollable rise in voltage. Now, that doesn't make inertia unimportant. Inertia still affects rate of change of frequency, protection margins, and the time available for controls to act. It means that in this event, more inertia alone wasn't the cure. So, why then did inertia feel like such a convincing answer? And it's because a synchronous machine was never only a supplier of megawatts. Its rotating mass provides inertia, but its electromagnetic behaviour contributes fault current, synchronizing torque, and system strength. Its controls can regulate voltage supply, dynamic reactive power. It can damp oscillations and it can provide governor response. The megawatts were visible. The missing behaviours were not. So no single replacement recreates that entire package, and the toolbox has to be deliberately unbundled. A shunt reactor absorbs steady-state reactive power. A STATCOM supplies fast dynamic voltage support. A battery provides rapid active power response. A grid-forming inverter can be designed to establish frequency and voltage behaviour. A synchronous condenser contributes voltage control, reactive power, fault current, inertia, and damping. The engineering discipline is to choose the required behaviour first, and only then choose the technology. The strongest evidence for that distinction is one of the expert panel's sensitivity studies. The model added 8 250 megavolt ampere synchronous condensers and distributed them across the Spanish transmission network using standard models and typical parameters. Now, in that model case, the added voltage control capability prevented cascade of generation trips, and the system reached a stable operating point. Now, this was a sensitivity analysis, not an alternative history, and it's not proof that the real blackout would certainly have been prevented. But it identifies the service cluster that mattered most in the model: fast, distributed voltage and reactive power control supported by the other behaviours of synchronous condensers. This is why the energy transition is also a control system transition, and it's happening on both sides of the meter. On the supply side, More generation responds through inverters, protection settings, right through logic and software. Whereas on the demand side, large facilities respond through UPS controls, transfer logic, protection settings, and managed reconnection. Both sides can now change state rapidly. Both sides share common settings across large fleets. Both can produce a correlated response that is individually correct and collectively destabilizing. Historically inherent behaviours must now be deliberately specified, tested, and coordinated. So before the next margin is spent, I would ask 6 questions. First, what functions are present, removed, or merely assumed? Second, how does the asset behave during a disturbance and not just in normal operation? Third, what happens if many similar assets respond together? Fourth, do the system models match the real settings, firmware, and commission configuration? Fifth, how and when will loads or resources reconnect after the event? And sixth, who owns assurance of the complete end-to-end behaviour? If the answer stops at the connection point, the assurance case is incomplete. Neither event supports a simplistic argument against renewable energy, data centres, or modern power electronics. Those technologies are part of the system we're building. The lesson is that an electricity system does not operate on energy alone. It operates on control. Every function we remove must be replaced by design, not assumption. Every protective action must be understood at both the asset boundary and the system boundary. Resilience comes from a rigorous understanding, measured behaviour, and whole system assurance. When every asset protects itself, who protects the system? As always, I thank you for your time today, and I look forward to seeing you in part 5, where we take a look at the role of the fire watcher. My name's Jason Broderick-Pierce, your host for Engineering Resilience. Goodbye.